Now that we have the big dog taken care of, and that's the cosine of a difference of alpha minus beta, we're going to use it to help derive the others. We did this in class the other day, but I thought I'd also put it on the video so that you can see it again if you want to review. Here's the compound statement. Remember, we had some key phrases here that kind of help us remember how all this occurs. That this O in the cosine says opposite, so make sure that anytime you have the cosine, these signs are opposite the signs in here. So if it's the cosine of a sum, it's the difference. If it's the cosine of the difference, then it ends up being the sum here. So that was kind of a little memory device that we could use to do it. We have this one already proven, the cosine of alpha minus beta, so we're going to use that to find the cosine of alpha plus beta. So what we do is we come up with a creative way of writing the cosine of alpha minus beta. Now the way that we can rewrite that is instead of having the cosine of alpha plus beta, we can write it as the cosine of alpha minus negative beta. So this is just a creative way of rewriting an addition problem into a subtraction problem, which means we can then use our cosine of a difference identity. So we're going to apply this identity to help us verify the cosine of a sum. So these are equivalent, but now we can apply our cosine of a difference. So that says take the cosine of the first angle, take it times the cosine of the second angle, which is negative beta, and then you have to add to it using our rule. If it's a cosine of a difference, it's always the sum on the back side, sine of the first angle, sine of the second angle, which was negative beta. If I pay attention to that, negative beta. So then if we write through our even and odd identities, that means this is the cosine of alpha, but the cosine of a negative beta is the same thing as the cosine of a positive beta, even odd identity, plus the sine of alpha, and the sine of a negative beta is the opposite of the sine of beta. That's an odd function. So if we finish our statement, the cosine of alpha times the cosine of beta, a negative times a positive is going to be minus sine of alpha times the sine of beta. Okay, so that's the first part. We just derived now the formula or the identity for the cosine of alpha plus beta. Next thing we'll do is we'll work on the sine. So what we already know is we know the cosine of a sum and a difference. So I'm going to bring that back up into our working memory here. We know the cosine of alpha plus beta is congruent to the cosine of alpha, cosine of beta, minus the sine of alpha, sine of beta. Now we're going to use that to help prove the sine of alpha plus beta. So the sine of alpha plus beta has to be changed into a cosine value. The one thing that we have available to us so far to help change sines into cosines is our cofunction identity. So what we're going to do is we're going to find a creative way of writing sine of alpha plus beta only using a cofunction identity. And the cofunction identity says the sine of an alpha plus beta has to equal the cosine of the other angle of pi halves minus the angle alpha minus beta. So now we're back to being able to use our cosine of a difference identity. I wrote the cosine of the sum. I probably should have written the cosine of the negative, so what that does is it changes to plus down there. So before we do that, we're going to do a little work on rewriting this expression. This is the cosine of, and this was pi halves minus alpha minus beta. And if you really want to get real detailed into that proof, then every subtraction can be thought of as addition. So this is the cosine of pi halves plus a negative alpha plus a negative beta, which allows us to regroup. And that's why I wrote it as addition, because we know addition is associative, and we can reassociate how we write those values together in parentheses. So then it's going to be the cosine of pi halves minus alpha then I want to put those in brackets, plus a negative beta. Well, I'm going to switch that back to just minus beta. So what we have is the cosine of two angles. This represents one angle. That's kind of like our first angle, and this is our second angle. So we can rewrite this as the cosine of the first angle, which is pi halves minus alpha, times the cosine of the second angle, which is the cosine of beta, but the cosine of a difference is always plus the sine of the first angle, which is pi halves minus 2. I'm sorry, that's alpha. Read my own writing. Times the sine of the second angle, which is beta. And I don't need a parenthesis for that. So just sine of beta. But if we come back and we apply some more identities, I'm going to just slide those down out of the way. The cosine of alpha, pi halves minus alpha is exactly the same if we apply a cofunction identity. That's the same thing as the sine of alpha times the cosine of beta plus, and the sine of pi halves minus alpha is the same as the cosine of the other angle, or the cosine of alpha times the sine of beta. And this represents the sine of our sum of alpha plus beta. So that took care of the sine of a sum, and that matches what we have for it. Next thing is we're going to find or derive the sine of a difference. I just got to keep moving stuff out of the way so I have room. The sine of a difference identity says it's supposed to equal alpha minus beta. It's supposed to be equivalent to the sine of alpha times the cosine of beta minus the cosine of alpha sine of beta. So we're out to prove that. So what we want to do is we want to come up with another creative way of writing the sine of alpha minus beta. So we're going to rewrite that as sine of alpha plus the negative beta, just as we did with the cosine. So now we can use our connection back to the sine of the sum. And the sine of the sum is, take the sine of the first thing, which is the sine of alpha, times the cosine of the second thing, which is the cosine of a negative beta, then add to it the cosine of the first angle, which is alpha, times the sine of the second angle, which is negative beta. And then we apply our even and odd function identities once again. Cosine of the negative beta, since it's an even function, is the sine of alpha times the cosine of beta, plus we got the cosine of alpha, and this is the sine of a negative beta, which is an odd function, which means it's equal to negative sine of a positive beta. And to finish that off, we have the sine of alpha, cosine of beta. Positive times negative makes a negative. Cosine of alpha, sine of beta. So that is our sine and cosine trig identities for the sum and difference. The next one that we're going to work with is our tangent of a sum and difference of two angles. Here's your compound statement, and then we broke it up, or I broke it up into two different statements. So the first one I'm going to do is I'm going to try to prove to you and derive the tangent of alpha plus beta. So to do that, I'm going to get it set up here. So the tangent of alpha plus beta, I have to relate it back to something that we already know, which is sine and cosine sum and difference identities. So tangent is always the sine of the angle, and our angle has to be alpha plus beta divided by the cosine of our angle. And again, that's just alpha plus beta. And now we can apply our sine of the sum and cosine of the sum identity. So the sine of the sum is the sine of the first, cosine of the second, then plus cosine of the first, sine of the second, divided by, now the cosine of the sum is cosine of the first angle, cosine of the second angle, minus sine of the first angle, sine of the second angle. Now we want it to look like the identity that they have in front of us, and that means we want to end up making, the key term to me is this one sitting right here. I don't want this term to end up being cosine of alpha, cosine of beta. I want to make sure it ends up being a 1. So the ploy that we do in the mathematical strategy is to take the top and the bottom of each of these fractions and create an equivalent fraction by multiplying by 1 over the cosine of alpha, cosine of beta. So on the top and the bottom, 1 over cosine of alpha, cosine of beta. Now these equivalencies here really are equal to 1. So I'm going to multiply this fraction by an equivalency of 1. I'll generate an equivalent fraction, only it will be in a different appearance. So if we start distributing this to here, we'll have the sine of alpha, cosine of beta, divided by cosine of alpha, cosine of beta. Then we got our plus sign. I'm going to distribute to the next term, which is the cosine of alpha sine of beta divided by, and this is going to be the cosine of alpha cosine of beta, over, now I'm going to work on the denominator side of this, so just change color to highlight and work on the denominator. We already had the cosine of alpha cosine of beta over, and then that was going to be over, this is how we devised it, so this will end up being 1, the cosine of alpha cosine of beta. Then we hit our subtraction sign, distribute to your next term, sine of alpha sine of beta divided by cosine of alpha cosine of beta. And now we're going to look at simplifying this result that we just wrote down. So what we have is we have some commonalities here. We should be able to simplify. This cosine of b divided by cosine of b is equivalent to 1. This cosine of alpha divided by cosine of alpha is 1. This one we said was a 1, and this is a 1, so this is a 1 times 1, or 1 times 1, just don't want to lose track of those because I got to retain that 1. And then we also have back here, nothing on the back side here that's going to reduce as far as the way we've been reducing the others. So equals, but what we can do now is if we identify the sine of alpha over the cosine of alpha, that's the tangent of alpha, then plus, the only thing left here is the sine of beta over cosine of beta, that's the tangent of beta, over, this reduced to our 1 minus, and this is a tangent of alpha, and this represented a tangent of beta. So now what we've done is we've derived the tangent of a sum of two angles. And to finish off this, what we're going to do is we're going to derive tangent of the difference, which is alpha minus beta. What we're going to do is we're going to do the exact same tactics that we had before in strategies, and that is change our subtraction into addition of the opposite. That still retains our same value, but now we're able to use our tangent of a sum, and that says you take the tangent of the first angle, you add to it the tangent of the second angle, which is negative beta, all over 1 minus the tangent of the first angle, which is alpha, times the tangent of the second angle, which is negative beta. And then we'll use our even and odd identities for tangent. Tangent is an odd function, so therefore the tangent of a negative beta is the opposite of the tangent of a positive beta, over, and then 1, and minus the tangent of alpha. But again, tangent of negative beta is an odd function, so it's times the negative tangent of beta. And therefore, the final result is our tangent of alpha minus the tangent of beta over 1, then these will be plus, negative times negative, tangent of alpha, tangent of beta, times the tangent of beta, which is the tangent of alpha minus beta. So in this video, I've attempted to show you that from the first trait function that we derived, the cosine of a difference, we're able to derive the sum, the difference of tangent and sine, and also the sum of a cosine. So now all of our main players are in play, and they're derived in, hopefully you can go back and look and see what kind of things there we can reinforce.